Hi everyone, we're kicking off today with a panel on artificial intelligence for space. I would like to welcome Dr. Nicholas Lungupe, who is a research engineer at ESA Spy Lab, Lorenzo, who is the CEO of aiko, and Professor Jaren from the University of Oxford. So thank you very much for joining us today. Everyone's really keen, got lots of questions, so feel free to keep writing them in that Q&A section, and we've got a Q&A portion at the end. So we'll start off with a short presentation from Jaren. So I will now hand over to him.
Cool, thank you. Can you hear me? Okay, I'm going to caution in advance that I'm a bit under the weather, so I apologize if there's anything which is not clear. While sharing, I can't see anything, so I can't see if there are any questions, so I can't see if you can't see me, if you can't hear me, so do jump in if there are any issues, if there are any questions during the talk. So I'm going to talk about machine learning in space. I'm from Oxford Computer Science Department. I'm head of the Oxford Applied and Theoretical Machine Learning Group. There are about 25 researchers working both on applications of machine learning in different domains, in space, in astronomy, in medical applications, in autonomous driving, and so on, as well as developing new methodology in machine learning, developing new tools that are then being used for these different applications, and using these applications to motivate development of new methodology and the new tools. So today I'm going to talk about some projects that we've had over the past few years on in space, in machine learning for space applications, in astronomy, and so on. So I'm going to start with a very quick introduction for what is machine learning, or more specifically, what is deep learning, which is what most people in the media talk about when they talk about machine learning these days. So deep learning is conceptually very simple models. If you give me some data, x1, x2 up to xn, and some inputs, these are x's, some labels y1, y2 to yn. For example, these might be images, these might be labels, cat, cat, dog, cat, and so on. Then I'm going to define a model. Given some matrices w and some nonlinear function, I'm going to define what we call a network. I'm going to take x, vectorize that, flatten that to be a vector, just do a linear transformation, multiply by w, fit for sigma, multiply by w2, and I'm going to get what we call y tilde. Then my objective is to find some w's for which these y tildes are as close as possible to yi for all the different i's. That's basically deep learning. Why these are called neural networks? Because you can look at each element in the vector xi as a node in a network, and you can look at each w as connecting these different nodes from one layer to the next layer. So deep learning is quite useful. It's simple and modular. It got huge amount of attention from practitioners, from engineers, and over the past few years, we've had pretty awesome software tools developed that allows us to scale with data and compute and get pretty impressive results. That if you look at machine learning from 10 years ago, it's amazing what we can do now. Deep learning at the same time also has lots of limitations. You can't really tell what our models know, what they don't know. There's also often perceived as uninterpretable black boxes, which are easily fooled, causing issues in AI safety. The deep learning often lacks solid mathematical foundations developed on top of ad hoc adaptations of previous methodology, and deep learning crucially relies on big data, which causes issues if, for example, if you're a scientist working on an application that doesn't have Google amounts of labeled data, then what do you do? How do you use machine learning? How do you use deep learning then? And we're going to talk about, I'm going to mention one way of tackling some of these questions, and then I'm going to talk about some applications that we use with these methodology tools that we're talking about over here. And for that, we're going to talk about the second big pillar in machine learning, which is probabilistic modeling. So if we had something called uncertainty, we could try to answer all these questions. What is uncertainty? Well, the language of uncertainty is probability theory. And specifically, we're going to talk about Bayesian probability theory that has its foundations in the 1750s. We apply that to information engineering, we get Bayesian modeling. So remember, a deep neural network just defines a function from input to output. So red line over here would be a neural network. Instead of having a single neural network, we're going to have a distribution of neural networks. We're going to have the blue one, the dark blue one, the green one. We have 4 neural networks. Each one of them might have a different probability. These ones might be more likely. These ones might be less likely to explain the data and so on. So that allows you to say, near the data, I'm confident my prediction should be so on. Far away from the data, my prediction could be anywhere. So Bayesian modeling is built on solid mathematical foundations, and traditionally was perceived to be fairly orthogonal to deep learning. And until a few years ago, people basically looked at this as completely non-overlapping fields in machine learning. And over the past few years, we've had lots of research on how to combine these two different things together, which allows us to get a Bayesian view or probabilistic view for deep learning. So let's say you give me CO2 levels in Mauna Loa, Hawaii, over the past 40 years. I center that, normalize it, fit a neural network, and you ask me what will be the CO2 levels in 20 years' time. Neural network is going to give me a very dense, sensible prediction. Obviously, it's not going to be this value. But the same neural network with a Bayesian view, where we look at these distributions of all the possible futures of might happen, then we see the model still says something very stupid, but it also says it has no idea. Each shade over here is half a standard deviation of a predictive uncertainty. So the model basically says it could also be anywhere over here. So what can we do with that? We can look at deep learning with small data. Just to make sure, can you still hear me? I didn't lose you. Can someone jump in and just tell me if you hear me?
All fine.
Awesome. Okay. Because as far as I know, I'm talking to myself. What can we do with this? We can do deep learning with small data, interpretable AI, safe AI, that sort of the fun stuff. So let's look at deep learning with small data. This is a project that we had with my student Lewis Smith, as well as collaborators Mike Walmsley and Chris Lintert at Oxford Physics and the Zooniverse Citizen Science Project. The idea over here is that how do we build the astronomical catalogs that we use in the field of astronomy? Well, we have these huge sky surveys that collect lots and lots and lots of data, lots and lots of images of galaxies. And then we need to build a catalog of all the galaxies and their properties. Is that a smooth galaxy, a featured galaxy? And traditionally, if you look at how these catalogs used to be built in the 17th, 18th century, you would have scientists sitting there making an observation and publishing that observation with those characteristics, those properties in a journal. And then as it started getting more digitized and started collecting these things using computers, you would have scientists going picture by picture, labeling these. Is it a smooth galaxy, a featured galaxy? The issue is that the recent sky surveys, we have so much data we can't do that even, because we just have billions and billions of galaxies. So how do we collect all of those? Like, how do we build those catalogs? So what the field started doing was using citizen science, using crowdsourcing to get these things labeled. But now we have even so many images that we can't even get crowdsourcing to label all of these. So what we do now is try to do machine learning. We try to build automated systems to classify this. Is that a smooth galaxy, a featured galaxy? But we don't want to miss all the ones that we haven't seen before, that we never saw anything like that before. We don't want to just say, oh, that's smooth, because my system just doesn't know anything better. So we combine citizen science with machine learning. We take machine learning models and we ask them, what is your prediction? Is that a smooth galaxy or a featured galaxy? And based on the uncertainty, based on the confidence in the prediction, we decide whether to trust that or send it to the citizens, like the crowdsourcing, send it to volunteers to label that. And then we collect those labels and then we update the machine learning model. That's called the human-in-the-loop machine learning, or human-in-the-loop active learning approach that we use for galaxy morphology classification. So this was published in the monthly notices of the Royal Astronomical Society a couple of years ago. Another example, interpretable AI. This is work with another student, Adam Cobb, done with NASA Goddard while at NASA FDL. Over here, we looked at using Bayesian deep learning for exoplanet atmospheric retrieval, trying to solve the inverse problem, which is if you give me a spectrum, then the task over here is we want to find what are the different atmospheric compositions for exoplanets. And doing one direction is very easy. If you tell me the atmospheric composition, I can tell you what the spectrum should look like for my satellite, for my telescope reading. The issue is that if you give me a spectrum, try to reverse engineer that to find what the atmospheric composition would have been is more challenging. What people use in the field are approaches like nested Monte Carlo or something, which are very, very slow. So again, these things, for example, wouldn't work with a newfound like many observations for exoplanets. So what we looked at over here was building interpretable machine learning tools that can solve the inverse problem. To give it you give it the spectrum of an exoplanet, and it can give you a distribution over the different like the atmospheric composition for the different elements, for example. Next one is talking about safe AI, uncertainty in computer vision. So we have different types of uncertainty. We have aleatoric uncertainty, which captures inherent noise in the data. We have epistemic uncertainty, which captures the model's lack of knowledge. For example, if you have this picture, I don't know how well you can see this, but if you have this picture, let's say so this is a picture taken from a dashcam, autonomous car, that has to classify each pixel, has to say that's part of the sidewalk, that's part of the road, that's part of a traffic light. You can see that sometimes these models fail. When those models fail, you would want your model to tell you where it failed, so your car doesn't take hard left into the traffic light over here. And this sort of tools could be used, so this was published at NIPS with Alex Kendall. These sort of tools could be used, for example, for settlement detection. So this is another project with another student of mine, Tim Rodner, published at AAAI with the work done with ESA while at FDL Europe, where they took different modalities from Sentinel-1, Sentinel-2, and tried to combine these things together to predict the segmentation map of settlements in regions where we don't have good mapping, for example. And the same tools for uncertainty could be used over here to tell you how confident are we that this is a settlement and not some spurious mound, for example. So last example that I have over here, I have a feeling I'm a bit over time, is machine learning in space, literally machine learning in space. So trying to do flood detection in orbit. So if you've seen the past few years, we've had some seriously fairly big problems involving floods in many parts of the world, causing some concern about how can we actually monitor this and give better first response. So this is an example of a region before flood, and this is a region after the flood. And what we would often want to do is basically be able to find a flood map saying this is underwater, and be able to send it to first responders in order to reduce the time for them to give help. So can we give them more accurate and automated image analysis in the field? The main issue is that at the moment, usually it takes about a few days before the satellite goes over the flooded region. Then it has to downlink all the data, and then someone has to sit down and analyze the data and label or use the existing approaches, but it's a very lengthy process to even get the flood maps before someone can attend to them. So what we looked at in this project over here is it feasible to do flood detection from orbit? Can we take CubeSats, which we might have constellations of CubeSats surrounding the Earth, and always you might have some CubeSat somewhere above you. And can we just use those CubeSats with low resolution images in order to get good flood maps that then could be downlinked into a ground station, even a field ground station? And we actually found some really nice results. We found that just from like very noisy sensor readings from these, from the sort of instruments that you have on these CubeSats, we can get fairly good prediction for flood maps, useful enough that hopefully they could be used in emergency situations. So this was published at Nature Scientific Reports, again with student Lewis Smith, I mentioned before, also with many collaborators together as well with ESA while at FDL Europe. So finally, yeah, that's a picture of the group from a few years ago. We're much larger now. We're basically researchers coming from academia, Oxford, Cambridge, Cape Town, Mila, Toronto, Amsterdam, industry, Google, DeepMind, and Twitter, and many others. And we're actually hiring. If you're looking to do a PhD, if you're looking to do an academic visit, if you're looking to do a postdoc, then just go on the website and look at what we do and look at whether it looks interesting to you. Thank you. How do I stop the screen sharing?
Thank you, Jaren. That was really interesting. We will do Q&A at the end with everyone together. So the next one up will be Lorenzo from aiko. So I welcome him to the screen. So I will hand over to you now for your presentation. Thanks, you
Zoe.
very much.
Thank you. Can you hear me well? Hope so. I'll just share the screen in 1 second. All right, so I hope you can hear me well, and thank you for joining in today. And well, I'm Lorenzo, the founder of aiko. We are a Diptech company working in the field of artificial intelligence for space. And let me guide you through how the industry is moving towards adopting these technologies of AI and automation for space. So just to give you a recap, aiko is a deep tech company. We are trying to be the leaders in artificial intelligence and automation technologies for upstream space applications. This means that we're working on problems in two directions. The first one is, how do we put machine learning and other AI technologies on board satellites to make them more intelligent in this case? Or how can we support the operators on the ground, the classical people that are in the mission control center? So when you have seen a couple of movies of people taking control of a satellite from those big screens, the question here is, how can we support these people and making sure they can improve or we can improve how operations are carried out in space missions. The real goal here, as an automation company, as we are, is pushing for the reduction of costs of operations in space missions. Let's not forget that operations in space are one of the top 3 costs of a space mission. So really pushing for automation there can improve and can help lowering these costs. Our deep learning technology is at TRL9. It means that we have already flown in space on a satellite. This was in 2019. We will fly more, and you will see it later. And at the moment, we are collaborating with many industries across Europe and with the space agencies, of course, Italian and European at the moment. aiko at the moment is 20 people in the team, and we look forward to be 27 by the end of this year. So if you are a data scientist, engineer, business developer, anything, pass by our website, send us a CV, and we'll talk. So let's have a look at the vision of aiko, how we're trying to do here. We're really pushing for the adoption of artificial intelligence in space. Maybe space is one of the fields that have lagged a little bit behind in the adoption of AI. Many different other verticals have already adopted these technologies. And our role as a deep tech company is to make sure that the ecosystem is adopting these new technologies. Particularly, what we're trying to do here is building an AI ecosystem that will support autonomous operations in different categories, in different verticals of the space ecosystem. We start with spacecraft automation. We believe that is the key place to be in at the moment, because spacecrafts can be improved in terms of capabilities thanks to AI, and in terms of lowering the cost, as I was saying before. But we will also apply our technology to other verticals, like astronaut support, so supporting the operations of humans in space, and also lunar and Martian applications, so trying to really push for the automation of the moon bases or the Mars bases when we will get the chance. Of course, we will also have a look at using our intellectual property also in other verticals, like drones, stratospheric platforms, and robotics, which are fairly close verticals to space. Just to give you an idea on what we're focusing on at the moment, we believe that we need to automate how spacecraft operations are carried out. So we're working at the moment in single satellite automation, really trying to have a fully autonomous satellites in orbit. But we are already internally working on constellation and cooperation management between different spacecraft. So things like formation flying, but also coordination between different satellites in different orbits. So trying to synchronize and coordinate observation, for example. This is supposed to be one of the key new enablers in new ways on how space missions are carried out. And later on, of course, we will also push our technology to the terrestrial domain. Concerning astronaut support, there are many things that can be done here, from smart products that support the life of the astronauts, smart products that support the monitoring of the stations and the habitable modules in which the astronauts live, and assistance and so on. The last point that is seeing quite a big interest in deep learning and other automation technologies is navigation. Generally speaking, deep space technology, in particular visual navigation, is really ramping up. The visual navigation domain at the moment is quite competing with other technologies, and we think that this is a potential innovation field. So I have a look, just to discuss briefly on our technology. The ecosystem we are building is based upon our AI automation software, which is Mirage. Simply put, you put Mirage on board the satellite, you put Mirage on the mission control center, and you really start to automate the operations of your mission. And what it enables is not just a reduction of cost, but your satellite becomes able to understand what is happening during the mission. It detects events and starts to be able to reason on how we can react to these events without the need of ground control to send commands to the satellite. And for us, the Mirage ecosystem is really looking forward to grow in many different directions. We are really trying to innovate as much as possible in this upstream space domain. So really having this AI ecosystem support Earth observation applications, telecommunication applications, navigations, and later on also astronaut applications. But we also believe that the hardware scenario in which satellites are flying, or that satellites are adopting, is really changing. And we need to support all kinds of new hardwares that are coming to space, like accelerators, GPUs are starting to fly in space, CPUs, and so on. And as a last direction of growth, we're pushing for Earth observation platforms, so of course, telecommunication platforms, and later on also traditional platforms. Just briefly on our company, there are three things, and I see many of the discussion that we just heard really resonating with what we're trying to do. First of all, trying to provide state-of-art artificial intelligence to the space ecosystem. Really, as a deep tech company, the only way to grow and to have a position in the market is to make sure that you're able to provide the latest algorithms available. And let's remind ourselves that AI algorithms are changing every couple of months, and you get a new algorithm, a new technology, and you probably need to substitute many of the algorithms that you were already using. This is our key role. The second role for us is really making sure that we're able to push for the use of AI on embedded systems, in this case, space and satellites. So we're really looking forward to grow in the direction of being able to optimizing and customizing the networks and the other AI algorithms that we do, deploying those on those limited computational resources that we have on board. The third point is also quite important. AI at the moment is still seen as a black box. It's still seen as something that we cannot rely on to do complex operations or complex activities. And we want to break this barrier. The goal for us is to build safety-critical AI. So we're working on robustness analysis, validation techniques, explainabilities, methods, and techniques to make sure that our partners can adopt AI with less preoccupations and be really trusting this technology. Just to give you a couple idea on how alive the European space ecosystem is with respect to AI, we have many different activities going on at the moment where we're really trying to push AI in three directions. One is visual navigation, as I was saying. Second one is the automation of Earth observation platforms. And the third one is the automation of telecommunication and constellation platforms. Briefly, and this will be basically the last slide, where are we as a company? Where are we in terms of demonstrating in orbit such technologies? We've flown in 2019 with Satellogic. I think this was the world first. Deep learning demonstration on our Earth observation satellite. We will fly this year on a SAR satellite, and we're going to validate in orbit next year our full capabilities for the full automation of a single spacecraft. Later on, 2022, we also have 2 joint ventures coming up for Earth observation and telecommunication constellations. All right, so as a deep tech company, we need a crazy good deep tech team. So we're pretty young, looking really forward to grow, collecting many talents from around the world in scientific and STEM disciplines. So again, feel free to submit a CV or a spontaneous application on our website. And thank you. This is aiko, artificial intelligence for our multiplanetary future.
Thank you very much. That was really interesting. I really liked hearing about how you can use AI with human exploration as well. So that was an interesting aspect and different to what we've just heard in the previous presentation. So I would now like to invite Nicholas to the screen, and he's going to give a presentation from ESA's Phi Lab on some of the work they do there. So I'll take it away.
Hello, good morning all. Nice to meet you. I will switch off my camera. I'm connected with my cell phone, so basically it will be better for you if I stop the camera, and then I will share my screen. Just a second. That works. Okay, you should be able to see it, right? I hope yes. So nice to meet you all. I'm Nicolas JP. I'm with the Phi Lab Explore Office, which is part of the Earth Observation Program at Aidh. We are based in Esrin, in Italy, nearby Rome. And today I'll give a talk on AI for Earth observation and the initiative that we are leading, and with the idea to bridge the different communities, the AI and the Earth observation communities. So indeed, we are talking about an AI revolution, and we're talking about self-driving cars, Go, robots that pretend to behave like human beings. And it's true that here we have the convergence of three fields. We have an overwhelming amount of data coming mostly from internet. Maybe you've heard about the ImageNet, which is a very large collection of image pictures with labeled. We have also an increase of computing capabilities. We have mentioned the GPUs, and it's mostly driven by Smurlo, the fact that the number of transistors per unit increase every 2 years and doubles every 2 years. And we have also the algorithm, which are made by GAFA, Google, Facebook, Amazon. Maybe you are familiar with PyTorch, TensorFlow, and so on. And indeed, for Earth observation, we'll mostly speak about computer vision image, and indeed we use deep learning, for example, to infer what is within the image. So here we have cats and dogs for the classification, but after that we'll talk about something more interesting, let's say. And it's true that for this black box we have still some issues that was mentioned by Jaren and Lorenzo. We have an issue about trust, and actually indeed this is very easy to fool this kind of algorithm. You just need to, for example, to add some noise, and obviously the output will be very different from what you expect. You can add, for example, a banana over cats, and the output might be quite different from what you expect again. We are looking for more explainability. We are looking as well for ingesting physics-aware information within the AI toolbox, and this is a true research field actually. There's a lack of reliability, as we mentioned, and it's so dependent on the data that you ingest, and to work on outliers and out of the distribution of the input and try to see in the causal effect of this outlier to the output is something which is also very interesting, and we are looking at this kind of field because this is very important for further adoption of AI. And indeed, for Earth observation, we are really at the rise of this field, and here we want to use AI as a tool to get more insight on the planet Earth. It concerns the ocean, it can be ocean bloom, forest loss, it can be about the cryospheres, or whatsoever the topics that are very useful to understand. There is a boom of deep learning in remote sensing, and here you can see with this bar chart the number of papers regarding deep learning in remote sensing, and we have an exponential numbers. And indeed, here we want to do many things with AI. We want to do prediction, detection, classification, big data analytics. We want to enhance the image that we have from the sensors and get some super result image. We can do also emulation, parameterization, so replace any complex models such as radiative transfer models with simple, let's say, and very efficient machine learning models. So we are talking here about emulations. We hope to do data science, and as it was mentioned by Lorenzo, we are also moving AI at the edge, so to have some onboard autonomy and to have some onboard decision in inference. At Aidh, we are building a set of satellites together with the European Commissions, and maybe you are familiar with the Sentinel mission. Sentinel-1 is a synthetic aperture radar that can penetrate the clouds and work day and night. We have Sentinel-2, which is a multispectral observation mission, so it's providing images at 10 meters on the ground. You have Sentinel-3, which is a satellite dedicated to the ocean with an altimeter, with some sensors to measure the sea surface temperature. We have now also the Sentinel-5P, which measured the atmospheric content, Sentinel-6, which was launched a few months ago, which enabled to measure the topography of the ocean. On top of that, we have the so-called Earth Explorer from ESA. We have Goche, which measures the gravity, SMOS, which measures the soil moisture and also the salinity of the ocean. Curiosat is for the cryospheres. Swarm is for the magnetic fields. We have Aeolus for the wind. We have Earthcare, which is for the cloud and aerosols. Biomass, it would be for the biomass, and Flex is measuring the fluorescence. So anyway, we have a set of satellites which is now on the sky, and eventually we want to do AI to fuse all this information coming from that sensors, not forgetting also the information that we can retrieve from social media or from nanosat or whatsoever the source of information. So indeed, here we have a data cube of Earth observation data, and from that data cube, we want to get some insight on the planet Earth and get some, for example, some example about the crops, the oil palm, the ships, or whatsoever the thematic information that you could retrieve. So here, after that, I will just give you an overview of some topics we are currently addressing at the PhilLab, but this is very few examples. Here, for example, we want to decipher and detect all the infrastructure in desert area. So basically, we do use a stack of Sentinel-1 images, which is radar, and thanks to deep learning and UNet, which is an encoder and decoder frameworks, then you manage to detect all the bedding in a given area. We are trying also to do big data analytics, for example, counting the number of, for example, plane over the airport, do change detection, and you have an example here relevant to the Wuhan due to the COVID on the bottom left. On the top, on the right, you can see some example where we try to extract the percentage of oil storage on oil tanks, and you can do that also with machine learning. We are also working with different partners, such as UNICEF, WFP, where they conduct, for example, some drone campaigns. And here the idea is these drones actually took some pictures on different crop fields. And we want to expand that information thanks to the Sentinel-1 or Sentinel-2 data. So we are really here at the fusion in between the drone and the satellites, thanks to AI. We are doing also some CI charting, and as you may know, this activity is being done by analysts actually who analyze this kind of image that you can see on the top left. So you have some guys daily who are looking at this image for now and try to decipher where are the CIs. And we are building now some algorithm that may enable in the future to produce automatically this kind of informations. We also do super resolution, as I mentioned. I mean, this topic is very active, and here on the top you can see some improvement can be provided by GAN, which is generative adversarial networks, and we are trying to apply more or less this kind of techniques to do the same, but for the Earth observation, we can do also a multi-frame super resolution, so using a stack of low resolution product and get a higher resolution product. We have also we organize some challenge, and one will be out in the coming months. It's around the Seeing Through Cloud projects, in the sense that For example, you may have a stack of Sentinel-2 images, but Sentinel-2 actually may suffer from crowds. And basically, if you have a stack of Sentinel-1 images collocated to the Sentinel-2, then you can maybe, in the case of clouds, you can maybe infer what could be the Sentinel-2 images, even though it is polluted by clouds. So this is some kind of fusion in between the radar images and the optical one. We can do emulation, as I mentioned. I will go fast. Actually, having some data set is something which is very important for our field. And because most of the algorithms that we use are actually supervised algorithms. So getting annotation is very important, and to involve the crowds is something which is quite relevant to have some high quality information. So we have been working on different projects, such as the game.io. It's more or less like a Tinder that you may know, and basically you have a question and then you click left and right depending on if the answer is correct or not, and that you get all the information from this smartphone app, and then you can create some database. We are working also with some company in Europe where we do some gamification and to get some annotation. So you may look at this crowd and machine project with Blackshore, where the idea is to use the crowd to annotate some very high resolution images, collect some information, and use that information to do inference at scale using, for example, Sentinel-1 or Sentinel-2 images. So we develop different tools that enable you actually to access these Sentinel images, and you may look at EOLearn made by a partner in Europe, Synergize. We are also developing some toolkits to get some analysis-ready data, which is very important, especially when the data is complex, such as the Sentinel-1, which is actually radar images, so it's not so convenient, let's say, for newbies to access that, but here now you have some tools to really ingest very easily this kind of images. As it was mentioned by Lorenzo, we are now doing AI at the edge, so with the idea that you put some inference capabilities on board the satellite directly. In September last year, we have launched the FISAT-1, which has an hyperspectral sensor on board. So hyperspectral means that you have a very big numbers of bands collected by these hyperspectral sensors, and obviously you have some limitation due to bandwidth and the data that you can transfer up to the ground. So the idea of this FISAT-1 experiment was to do crowd detection directly on board, and to transmit the information which were not polluted by the crowds. So you do directly inference in space, and basically we use a VPU made by Intel, which is a Myriad 2, and as you can see on the image, I mean, this chip is very, very small. It can hold in a hand, and it has very low power consumption, only 1 watt, which is very, very important, but still with good performance. And so, as I said, AI is a tool for us. We want to accelerate the time to insight for Copernicus. We want to tackle many fields. It can be prediction, detection, classification, fuse all this information all together, do emulation, ingest some physical aware knowledge within the AI box. We are talking about AI at the edge, and also, as I mentioned here, the idea for ESA is also to bridge the different communities, to bridge the AI and Earth observation. So now we have many EO practitioners who use AI, but also it's very important to go in the other direction and make this EO data very easy for the access to these AI experts. We are running some challenge. So you may look at this website, AI4EO.eu. We have launched lately a challenge around air quality with the idea to dump sample the data from Sentinel-5P in the coming days, and in 2 weeks from now, we run another challenge, and so please stay tuned. And if you have any question, please let me know. You have my email address here. So that's it. Thank you very much for listening.
Thank you very much. That was very interesting. And we have a lot of questions, and we actually have about 20 minutes to answer all your questions. So keep them coming in. We have quite a bit of time. So I'm going to invite Lorenzo to come back. I'm also going to invite Jaren to come back. If you could make sure your cameras are on so everyone can see you. And we will start with our first question, which is about machine learning in space. So what pros or cons do you see of performing the training phase in orbit versus on ground? Is uplink a bottleneck for uploading model weights or training data?
I don't know, guys, who's gonna talk first here. I mean, I
Go ahead.
I can give our perspective just for a couple of things. So first of all, we didn't. At least what we believe at the moment is that it's quite difficult to do training in orbit. So really, what you're looking forward to do is mainly do training on the ground and then upload the model in orbit. This is in general. We are looking forward at some applications that involve training in orbit, in particular reinforcement learning in orbit for decision making. But this is quite different with respect to doing, for example, payload data analysis in orbit. In those cases, you likely do training on ground. The model size, it is a bottleneck for uploading it into the spacecraft. So especially machine learning itself needs to be iterative in the training. So you want to be able to re-upload the model if something doesn't go well. And the size is quite a bottleneck, depends on the configuration of the mission itself. This is our take.
I can comment, but I'm actually curious to ask you a question based on what you just said now. But before that, I'm going to comment quickly that there's lots of research on quantization and compression for machine learning models, including pruning and so on, that allows us to take huge models and remove 99% of the weights and try to preserve as much accuracy as possible. That's, I think, in practice, shouldn't be a concern. What I would be much more concerned about is robustness of models and robustness of training and deploying things without being able to actually test them properly. And training something in orbit, including reinforcement learning, in my mind, is a very, very risky thing because it's much more difficult to actually validate that the thing that you're deploying does what you want it to do.
Absolutely agree. Absolutely agree. We're not talking about something that is risk-free or actually quite risky, but in fact, for us, this is not even a commercial stage. It's just R&D trying to understand how we can put reinforcement learning on board a spacecraft, if at all, actually. So yeah, I completely agree.
A question for you is, like, we had discussions with colleagues at ESA, like Athena project, for example, trying to look at prioritizing, building schedules for like prioritizing like observations, and we were looking at what's the best way of doing that, and they were very keen on doing reinforcement learning. And like, do you know of any application that actually requires doing reinforcement learning in orbit?
So the major applications that we can see at the moment is where you are flying in a scenario. Well, we're talking about some sort of proximity operations. So maybe especially towards asteroids that you probably don't even know their surface feature from ground at the moment, or maybe some sort of application of in-orbit servicing. But really, there is no, to my opinion, at the moment, there is just the indication that there might be something to do with reinforcement learning there, but there is not an indication whether reinforcement learning will outperform other approaches of AI, or not AI based. So this is something still under investigation, I think. Basically, the goal of reinforcement learning is really to push an agent to explore and exploit the boundaries of the environment, and the things that you traditionally want to do in space are not really suitable for pushing the boundaries of this exploration of the environment. So
I don't think you want to explore the environment if you're
exactly
space, yeah.
Exactly. You want to something that is safe, robust and safe. Absolutely.
So we have our next question, and this one's aimed at Lorenzo, but if you feel you can jump in and answer as well. It was to give an example of some of your projects that AI is used in human space exploration and the challenges that they might be facing. So I'll throw it to you, Lorenzo, and then if Nicholas or Jaren have anything to add as well.
Yeah, absolutely. I can cite the project that we have on the Artemis program with the Italian Space Agency and Thales Alenia Space. Here we're trying to understand how we can basically create kind of an IoT architecture where we have different sensors spread out in a moon-based, or at least in lunar habitat, and trying to get information on how the astronauts might be operating, how, for example, the presence of the astronauts in specific position and portion of the modules, how the astronauts are interacting with the external environment, gathering all this data with sensors, and then trying to process this data directly in orbit, in orbit, in this case on the moon, is an application. On our side, we are starting to look at health support with AI for astronauts, but this is a very tricky field. So at the moment, we're just investigating this very broadly.
On that question, I don't have any particular comments. So within the Earth observation program, obviously, we are looking at the planet Earth. So sorry, I don't have any further comment on that question. Maybe Jaren.
What was the question again?
So it was about human exploration and how AI could be used, if you know any projects.
Generally speaking, the idea is that the farther you go, the more independent you would like to be, because of the latency that it takes you to take decisions if you need to interact with the ground. No? So whether it's human support or whether it's robotic automation, the idea is the farther you go from Earth, the more difficult it is.
One of the discussions we had were about deep space missions. For example, if you send, I think it was like one of the, I don't remember the details, but it's similar to what you're saying, that you basically need to take, you can't have like human control over the operations anymore, so you have to automate that, including the data processing, including deciding what to acquire, what to even like observe, and then from that deciding what you even want to downlink back to Earth, because that by itself becomes extremely expensive for deep space missions. So you want to automate. It's not even just a matter of like automating the flight trajectory, or that you can do in advance, but to decide what is scientific value to send back to Earth, it becomes new challenges to try to solve.
So we've got another question. I'll throw this to Nicholas. I know he's there. His video isn't working currently, but please feel free to ask him questions as well. He's still here. So my question is, AI is still in its infancy with a long way to go before we crack the singularity. What is the most out there application of AI that you would want to pursue, imagining that we have advanced AI?
Nicholas?
Can you hear us?
Can you just repeat the question? Sorry, I didn't hear very well.
So
Sorry about that.
AI is still in its infancy with a long way to go before we crack the singularity. What is the most out there application of AI that you would want to pursue, imagining that we have advanced AI?
Well, in the field of earth science and so on, I think that what is missing on our side at Aidh is really to bridge the gap in between the scientists who have developed some very nice model, radiative transfer model or oceanic circulation models and so on, and bridge that to the neural networks and deep learning stuff. So we're really pushing towards the physical world and explainability to ingest that so that people may make really informed decision that can be trusted and explained. So that will be our next step, is to fuse the physics and to get more explainability and trust in the model really. And I think this was mentioned already by Lorenzo and Jaren in our talk, and this is what we expect from the community. And that will be a game changer.
Also, just to clarify, I think I should have mentioned that at the start of my talk. When we say AI, we don't mean AI in the sense of like science fiction, like strong AI, artificial intelligence. We mean AI in the sense of machine learning, in the sense of statistical tools, statistical models that can be fed data, observations, and be trained to fit functions to predict some targets that you had in the data. Reinforcement learning that we talked about as well. Now, also is a statistical tool that just operates in a slightly different set of assumptions. I don't think any one of us is talking about AI in the sense of singularity that was hinted at in the last question.
So we'll move on to the next question, which again, this one's for Lorenzo. And I think it's to do with what you mentioned earlier in your presentation. So what do you think about applying AI technology to less safety critical phases, such as satellite development or manufacturing? So I think this follows on what we talked about a little bit earlier.
Yeah, absolutely. So in fact, as aiko, well, aiko core domain is the automation of operations, but we already noticed and we're already working on the use of AI before and after, let's say, well, before a mission is launched. So the activities of assembly, integration, and testing of a spacecraft can be helped by AI, just mainly because we are generating an incredible amount of data on ground during testing. And there are many times very complex equipments that you're testing, and data science in general, supervised, unsupervised methods are already being used in this direction. So I can give you a high-level example. We're working at the moment on analyzing the ground data testing of a spacecraft with one of our partners, and here we are using unsupervised methods to basically help the engineers in testing the spacecraft, in particular one equipment, and trying to understand whether they can change some of the design choices that they did thanks to the analysis that we are doing. So AIT, so assembly integration and testing, is a huge word there. There are some ideas of using design, AI-enabled design tools. A quick example there is genetic algorithms and, generally speaking, evolutionary algorithms to browse very quickly towards all the different design choices that you might have during a space mission, ranging from the architecture of the mission, the design of the spacecraft, the selection of components of the spacecraft. Those are quite, let's say, well, the applications have been there for quite a lot in research domains. I don't know whether any companies are actively using these tools at the moment, but there is some idea. There are some ideas there as well. They fall within the optimization domain in general of a design.
So I will change pace a little bit and ask a question that's less tech heavy, and actually ask you guys, how did you get into the domain of AI? What is your background? Because we have a lot of students. We have questions about if there are hackathons on AI, if those are available, any you'd recommend. So I just wanted to get a little idea of how did you get into AI? How did you get into machine learning in space and that sort of thing? And what recommendations would you give to anyone that's listening in and might have that as a thought in the back of their head?
I think there are lots of resources online. Go ahead. I thought someone was
Please go, Jan.
Yeah, I think there are lots of resources online. I think I Google Summer of Code. I think is a good way of getting into this sort of coding, not necessarily AI, but a lot of these things can lead into like playing with tutorials and playing with different things that you have available online to get an idea for what these things do and what they look like and stuff like that. I can tell you that I find more and more that undergraduates applying to work, just applying to university, already like have played with these sort of things before they even start their undergraduate, meaning that it's pretty accessible now compared to what it used to be. And I just would encourage you to search online, find a tutorial, and just play with it and see what you can get, what you can do with it.
Yeah, absolutely agree on this as well, Jaren. I think, well, while I mean the mathematical background and the theory background is important, the online tutorials gets you up to speed, at least on the use of certain technologies. Maybe not really the understanding, but at least the use of certain technologies, and this is key. And to add up on that, try to do, if you're a student and you want to be part of this world of the AI machine learning world, do proof of concept, do some side projects, get your hands on these technologies as much as you can.
complete this message, I think it is quite important to have in mind that it's quite important to have some thematic field expertise and not really only on the data science aspect, because at some point in, let's say, in 10 years from now, I mean, all these tools will be available to anybody. So at some point you need to get some specialization and need to get some expertise on the data, which is still very important. You need to understand what is the data. I mean, it's not only some bits, but it's also some, there are some meanings behind, and you have to catch it and understand what you manage and you handle. So please keep that in mind, and do focus as well on this thematic expertise that you need to have in complement to this data science, if we can call it like this.
Yeah, and on the academic side, if you want to study these things, then if you're applying for undergraduates, then undergraduates in computer science and mathematics and engineering usually would teach you the tools to understand the mathematics behind and to be able to develop more, but also physics and other sciences. A lot of the PhD students that I advise come from backgrounds as diverse as computer science, mathematics, biology, physics, many varied different fields. If you're looking to do a master's, then there are lots of programs now that specifically teach the foundations for you to understand, as well as like all the recent methodology in machine learning and AI. There are lots of special, lots of one-year master's programs now that teach all the background that you need, as well as all the current methodology, current tools and techniques. If you're looking to do PhDs, then there are lots of really strong departments and universities around the world, in Europe, in the US, in Canada, in Asia, that would work on different fields within the field of machine learning and AI. And then if you want to work on different applications of intersection of machine learning and space, then there are lots of like physics departments, astronomy departments that are working on AI sort of things when they work on this astronomy or the scientific research question.
So I'll ask, this will probably be the last question, just to let you know what this will really help on their working group discussion. So that's why I've left this one till last. So given potential latency impacts, especially for mission critical systems, is it going to be better to have processing elements within the atmosphere, maybe as on a HAPS-based architecture instead? So that's the question. They're going to be doing working groups. A lot of it's based on these HAPS-based architecture as well. So if you could really look at that. And then we actually had a second question, which was about what are the uses for AI in HAPS? So if I ask you two questions in one.
Okay, so by HAPS, we mean the high altitude pseudo-satellites, I guess. I mean, I don't know whether we can confirm that or not, but I'll answer whether this is the interpretation.
Yes, it is.
Okay. So, well, in our opinion, there isn't much of a difference at a higher level with respect to a satellite or a HAPS, because they are doing similar things. I mean, they are observing something on the ground. Well, if we're talking about Earth observation HAPS, of course, what changes is the resolution, the spatial resolution that you get on ground, and this is completely different. But generally speaking, you're trying to process data, and you try to acquire data and to process them. Maybe one thing that changes is the connection availability. So possibly HAPS are quite more connected, I assume, with respect to a satellite. So if the latency between the ground station passes of a satellite is quite an issue when you want to do, for example, alarm generation, notifications, things that are really low latency applications. And this is an issue, and this requires autonomy on board. If the satellite is always connected, a geostationary satellite, for example, or in case of a HAPS, maybe you might have internet on a HAPS. Then the requirement for processing everything on board becomes less strong. And then it's maybe a trade-off between how much data you can send to ground with respect to what you can process on board. And maybe that's an interesting point of view to see. But basically for us, the amount of connection and the frequency of the connection and the latency that we have defines the trade-off between what we put on board and what we keep on the ground.
I'm not sure why it's a question of latency compared to bandwidth.
Exactly. I understand. I mean, the point is how much data you can send to ground. Latency only comes to play whether you have no constant connection, and then you want to make sure that your data is as quickly as usable as possible on the ground. So fire detection, things like that. Maybe you want to send down notification first and then the image later. But for our hubs, maybe it's.
I would also comment that with respect to a previous question about training on board, like machine learning in general, training specific, machine learning also inference, test time, like prediction, is compute intensive. And compute intensive implies that it requires lots of hardware and it requires lots of energy, meaning that if anything that we can avoid doing on board, we would try to avoid doing on board. If we can build a better, within the constraints of the project, if we can build a better downlink and increase the bandwidth, we will prefer to do that instead of doing the training and or testing on board. There are constraints like deep space missions where we can't increase the bandwidth, for example, or like in that case, the latency. There are constraints where, like CubeSats, where we have limited bandwidth, for example. So in those cases, we need to find how to use machine learning in a smart way to avoid doing lots of computations on board and then solve the problems. So I hope that somehow relates to the question.
Thank you very much. So that's all the time we've had for today. We have a lot more questions. You did a really great job with your presentations, and I'd like to thank you because everyone's been super engaged, and I think that's one way to start the morning, I think, with some nice AI in space. I think it's got everyone's minds just really blown. So thank you very much. We now have a short break for 15 minutes until 10:30. So I encourage all of the delegates to go to the networking area where we actually have you can meet your other delegates in 3-minute meet and greet sessions. And if you are interested in who you're talking to, you can extend your time there. So if you go there for 15 minutes, you can meet everyone. And there are also some of our organizers there you can talk to, and there are also some of our sponsors floating around as well. So meet back here at 10:30 for our keynote from Airbus. Thank you again to our panelists, and we'll see you at 10:30. Thank you very much.
Thank you, Zoe. Have a great day. Bye, everyone.
Bye-bye.